Alright, so our question for our project is, how will a system with no contact for moving object affect the efficiency of a system? And our hypothesis is, if a system that doesn't have any contact between moving objects, then we think that the system's efficiency will increase. We think this because the reason for low efficient systems is friction, and if we can eliminate the friction, theoretically, we should have a self-sustaining closed system.
Alright, so the purpose. So, we know a perfectly closed system is impossible, and we just wanted to see how close we can really get to it. And our initial thought was to eliminate friction, because friction is the main reason for energy to escape from the system, which makes it not closed. And so we came up with the idea of using levitrons, using magnets. And so using the north, because magnets have north and south pole, we can use the two north poles to repel each other to avoid all contacts between objects and in turn avoid all friction. And more importantly, we've never heard of anybody doing this kind of experiment before. We've never heard of people using magnets to create a system. And the core of our whole project is to observe where the energy is escaping in our system. Alright, so our procedure. For the control group, we just spun the top on the ground like that. And so we got a sheet of paper and we made 1-inch increments on it, and we tied a rubber band around it and we stretched out the top 3 inches from the starting position, and we let go and the rubber band would untie and spin. And so that was our procedure for the control group, which is the top on the ground. Alright, so for an independent variable, we're going to do the floating top on a levitron, and we do the same method as we did on the ground. We tie a rubber band around it, extend it out 3 inches, and let the rubber band unwind, and it's going to spin and it's going to levitate. It's going to spin like this, and we're going to hold it up and until it starts to levitate perfectly. And for both these, the control and the independent variable, we're going to time how long it spins for.
Alright, so our data for the top spinning on the ground was a lot more consistent compared to the top in the air. That is due to the fact that the levitron wasn't always perfectly level. Alright, so the average for our top on the ground was about 14 seconds, and the average for the top being in the air was about 30 seconds. Alright, as you can see on our graph, that the top spins double the amount of time than it spins on the ground.
Alright, so in conclusion, our hypothesis was supported by our experiment. We were able to increase the efficiency of our system by eliminating about 60 to 90% of the friction. We saw a clear pattern from when the top was in the air and when it was on the ground. The top spun for more than double the time while it was in the air down in the ground. Alright, so the big question is, why does the top spin longer in the air than on the ground? And the answer is simple. We observed that because air is a gas, the molecules are spread out a lot further, and hence they interfere less with the spinning top. And while the top is spinning on the ground, since the ground is a solid, and the molecules are much tightly packed, and so they interfere much more often with the spinning top. Alright, so we also had a few errors while we were performing our experiment. They include not spinning the top at the same speed every time, drafts in the air, and not a perfectly balanced levitron, which is the biggest error that we had. Although we had these errors, they didn't really affect our data that much, because even with these errors, we still proved that in the air, the top spun for a much longer time. For example, when the levitron wasn't perfectly balanced, the top would fall off faster because of the crooked magnetic fields, and the top would just fall off. And we predict that if the levitron was perfectly balanced all the time, then the top would spin easily 4 to 5 times longer than on the ground. Alright, so future experiments. To improve on this experiment in the future, we can do a number of things. Place a levitron in a vacuum chamber, so it'll take out all the air resistance, and we can really see how long the top will spin. Also, what we can do is design a method for spinning the top at a consistent speed every time. We can also get a leveled floor to make sure we reduce all the bumps while the top is spinning on the ground to get better results there too. And last thing we can do is have a perfect level of levitron so that the top will spin to its full potential.